Now let's revisit independence. This concept is one of the first concepts we talked about in this course when we talked about independence and dependence of vectors. And we've asked the question, when are some column vectors linearly independent? And we said that they would be dependent if they're not independent. Now we make that definition a little bit more formal for a collection of vectors, but we will start with our first definition, which of course uses the columns of a matrix A. So this is something that we have seen. The columns of a matrix A are linearly independent when the only solution to the equation AX equals 0 is X equals 0. No other combination AX of the columns of A gives the 0 vector. Now we know that the only time the only way to satisfy this condition, AX is 0 only when X is 0, is if the matrix A has a 0 null space. So this exactly happens when the null space of A is 0. In other words, this happens when A has full column rank. Now, why do we care about this definition? Because matrices give us a systematic way to answer the question, given a collection of vectors, can we say that the vectors are linearly independent? Or how can we say that the vectors are linearly independent? Well, we could put those vectors in a matrix A as columns of the matrix A, carry out reduction, and see whether every column of A has a pivot there or not. If every column of A has a pivot, it means that A has a full column rank. And if A has a full column rank, its null space is 0. And if the null space of A is 0, then we know that the only solution to the equation AX equals 0 is X equals 0. So multiple ways to think about the same thing and a systematic approach to answer the question whether a collection of vectors is linearly independent or not. This definition is not the standard definition you would see in the majority of linear algebra textbooks. The more standard definition is what I have labeled here as definition 2. It starts like this. The set of vectors v1, v2, vn, so some collection of n vectors, is linearly independent if the only combination that gives the 0 vector is 0v1 plus 0v2 plus 0vn equals 0. So if these v vectors, v1, v2, vn, are column vectors, then we could place them as the columns of a matrix A, and we will know that, this linear combination, or rather a generic linear combination here, x1 v1 plus x2 v2 plus xn vn, this would be expressed as some matrix here with columns v1, v2, all the way to vn. So these are column vectors, multiplied by some vector x1 all the way to xn. So this linear combination, that product that we have on the left-hand side, or that the linear combination that we have on the left-hand side, is a product of a matrix times a vector, and we want that to be 0. So we have some matrix, let's say V times x is 0, and we know that if we want this x to only be 0, we are asking for a null space of that matrix that is 0. So in the setting where the V's are column vectors, really you see that these two definitions are truly equivalent. But if you recall, when we defined vector spaces, we saw that two vector spaces a vector space could consist of something not column vectors. You could have matrices, you could have functions, you could have all kinds of elements in there. And still, this idea of linear independence defined in this context, so these vectors don't have to be column vectors. These just have to be elements of a vector space. And we can talk about linear independence because in a vector space, a linear combination is defined. Therefore, we can always go to that linear independent definition, or definition of linear independence, in the context of any vector space, not just columns, not just column vectors. But for column vectors, our practical way would always be this first definition, because it lets us compute in a systematic way. We stick some column vectors into a matrix, and we can answer all these questions of linear dependence or linear independence. So now, when we talk about column vectors, we have a very important example with this definition that we can explain. And it goes like this. Any set of vectors, any set of n vectors in Rm must be linearly dependent whenever n is bigger than m. Now, this is a very important statement, and we have to understand exactly what it says. So recall that the vectors in Rm, these are column vectors with m components. And what we are saying is that if we take n vectors with m components, where n is bigger than m, so for example, think, maybe I'll write that example. 3 vectors in R2 are linearly dependent. Seven vectors in R5 are linearly dependent. And this is guaranteed. If I take 7 vectors in R5, I'm guaranteed to have a set of vectors which are linearly dependent. Question is why? Why is this? So here, why? And the answer is actually quite simple. Take that collection of vectors. So let's take vectors v1, vn in Rm, and put them as columns of the matrix A. What are we going to have? So we're going to have the matrix A with its columns v1 here all the way to vn. Now, the v's, they have m components, which means that A has m rows, and obviously A has n columns. So A is an m by n matrix with n bigger than m, right? So A has fewer rows than columns. Well, let me even write that. A has fewer rows than columns. Well, then the number of rows gives us an upper bound for the rank of A. A cannot have more than m pivots. So A cannot have more than m pivots. Well, if A cannot have more than m pivots, then A cannot have more than m pivot columns. If A cannot have more than m pivot columns, then A cannot have n pivot columns, right? It is not possible for this n to be reached with pivot columns. In other words, A cannot have full column rank. Well, if A cannot have full column rank, then the null space of A is not just 0. So then the null space of A is not the 0 vector space. It has something more. There has to be, there are free columns in A. Those free columns give us non-trivial linear combinations of the columns that give us 0. So there are ways to combine the columns of A to obtain 0 for every free column. All right, now why do we talk about this? How is it important? So we know that when we have a vector space Rm, we cannot have more than m linearly independent vectors. The moment we take more than m vectors, they become dependent. Now, why is this important? So the next videos, I won't do them in all at once, they will talk about the true size of a vector space. So we're getting to this point where if we're talking about the vector space Rm, then this idea that we cannot have more than m vectors that are linearly independent gives us sort of a limit on what we understand to be the size of this vector space, the true size. These are all infinite sets, and yet some are bigger than others. For example, with R2, we can take at most 2 vectors that are linearly independent, and with R5, at most 5. In the next videos, we'll define basis and we will define dimension.